1989 from UT Lahore and joined Dr. A.P. Khan Research Lab in 1990. Later in 2011, he got his PhD from UT Lahore, sponsored by KRL. He served KRL for more than 33 years and retired as Director General Metallurgy Division in 2024. Presently, Dr. Amjad Ali is serving as an advisor to the National Command Authority Research and Development Board under the command of Strategic Planning Division. He has 20 international publications. He served as the General Secretary of Pakistan Advanced Materials Forum from 2020 to 2024 and conducted two international symposia on advanced material. Please welcome Dr. Amjad Ali to deliver his talk on the topic of Introduction to Aluminium Metallurgy.
Thank you, Doctor. In the name of Allah, the Beneficent, the Merciful, I am grateful to the organizers of the workshop for providing this opportunity to interact with young as well as seasoned scientists and engineers. My topic is an introduction to metallurgy, aluminum metallurgy, and it will be a recap of these segments, and I will start one by one. Aluminum was discovered in 1825 by Hans Christian Ørsted, a physicist from Denmark. After the discovery, it took more than 30 years to start the industrial production of aluminum. At that time, aluminum was very expensive and only affordable by the kings and emperors to use the cutlery. It was actually the symbol of wealth and prestige. But thanks to two gentlemen, that is from America and from France, who developed a new process for economic production of aluminum. And that process is known as high-herold process. The element aluminum, as you have already seen in pictures, both spellings are correct, so परेशानी की कोई बात नहीं है. Aluminum भी ठीक है, aluminium भी ठीक है. It has certain physical properties, and you know aluminum is darling of the designers and engineers all around the world because of its high strength to weight ratio. Aluminum is the third most abundant element in Earth's crust after oxygen and silicon. It has neon shell with 3 electrons in the valence shell. Its structure is already is a face-centered cube structure. The source of aluminum. The aluminum is, as you know, is the most abundant metal in the Earth's crust. In the last slide I said it is the third most element after oxygen and silicon, and from metals, it is the most abundant metal in the Earth's crust, and it is about 8.2% of the Earth's crust is composed of aluminum. The main source of aluminum is bauxite. Bauxite was discovered in 1821 by a French geologist, and he named the bauxite of the name of the village. There is a left box which is present in the southern France. What is bauxite? Bauxite is a sedimentary rock which is formed by the consolidation and cementation of sediments. It is a mixture of different minerals. As you see, these 3 minerals are of aluminum hydroxide, then there is iron oxide, and titanium, and ilmenite, and agates. So these are the mixture. About 30 to 65% content is aluminum, and that's why it is used for the production of aluminum. Bauxite reserves in the world are listed in this table. You can see it is, their main countries are China and other, but there is no Pakistan in it. So bauxite is present in China, bauxite is present in India, bauxite is present in Kazakhstan, Russia, but what is the problem with Pakistan? Do you think it is not present in Pakistan? Anybody? Not present? Yeah. Just have a look at the bottom line of this. With Turkey showing 63 million tons of bauxite. So let's see what is available in Pakistan. Sizable deposits are available in Pakistan in different areas like Kushak and other areas. And you can see here this single Kathapel, this is a single deposit which has more than 100 million tons of bauxite. And this is more than Turkey. But why Pakistan's name is not in that list? That's because it's a question mark on us, because we do not value our minerals and natural resources, and we do not know the potential in these minerals, these resources. We have to think about that. Regional bauxite prices are listed in this table, and you just remember the maximum value, that is 80 million, it will be discussed later. The global market of bauxite is 15.6 billion US dollars in 2022, and it is projected to grow to about 18.16 billion in 2030, with a compound annual growth rate of 1.7%. So this is the market value, and we are not mining it properly in Pakistan. Extraction of aluminum. So how we go for there are 4 steps actually. The first is mining, and we are not doing in Pakistan any proper mining of the bauxite. Then crushing milling. The third step is the dressing of the mineral for refining to produce aluminum oxide. And that process is known as the bare process. After that, we go for the smelting of the alumina, and we produce aluminum, and the process is known as Hall-Herold process. Bare process. Here you can see that they start from the crushing and milling, and then they put it in a pressure vessel, raise the temperature, add sodium hydroxide, and the reaction is like this. This sodium aluminate is formed, which is soluble in water. And because it is soluble in water, the other minerals present in the bauxite, like iron oxide and titanium oxides, they are not soluble in the water. So if you filter this substance, you will get red mud out, and you will only get the aluminum hydroxide. So one step is cleared. Then it is cooled to recrystallize. We add some crystals of aluminum hydroxide to form the aluminum hydroxide substances. This is later heated to about 1000 degrees Celsius to remove the water and get the pure aluminum. The reaction is, as you can see, the water is removed and aluminum is oxide. This is also known as corundum. So the next step is to Hall-Herold process. So what was the difficulty initially? Why was it very expensive? Because of the melting point of corundum, aluminum oxide. So do you know the melting point of aluminum oxide? Before I tell you the melting point, I will show you the global market of the alumina. Alumina is not only used for the aluminum production, but it is also used for other applications. You can see innovative coatings, transparent ceramics, and so much consumer electronics and other. And its market is projected to be more than 20 billion US dollars by 2030. The melting point of bauxite or alumina or corundum is more than 2000. And this was the actually bottleneck, that reduction was very difficult, very expensive, and that's why aluminum is very good. So the hard process use a compound called cryolite. Cryolite is basically sodium hexafluoroaluminate. Its melting point is about 1000 degrees Celsius. So when you dissolve alumina in molten cryolite, it dissolves and ionizes. Some other uses of the cryolite here. So hot and hot process, you can see the alumina is dissolved in the molten cryolite, and then in an electrolytic cell, it is reduced to aluminum. You can see the graphite electrodes, cathode which is negatively signed, and then there is the positively which is fused coke, and alumina is dissolved in the molten cryolite. When electrolysis takes place under the action of the high current, you will see this one 300 kiloamperes at a low voltage, and you use 50.3 kilowatt hour for 1 kg of aluminum. The ions are heavier, more dense, they are moved towards the electrode, and then they are tapped out from the cell from bottom. The cell reactions are, you will see at cathode, aluminum ions are reduced, whereas at anode, oxygen ions are oxidized. The overall reaction is you get pure aluminum and carbon monoxide. And if there is excess of oxygen, you get another type of another reaction. You can see. So this is the aluminum, molten pure aluminum you get here. So what is the value addition from mold ore to metal? I showed you the bauxite price, that is $80 per ton, and then alumina $605 per ton, and if you get aluminum, that is 2,620. So value addition is about, you can see this red line, 33 times value addition. So if you use your local ore at bauxite and you produce alumina or aluminum, up to the aluminum you can get 33 times value addition. Something very strange, Pakistan $448,000 to export the bauxite, and then spent $383 million for the import of aluminum. So if they have developed bare process in-house, they could have already converted it to aluminum themselves. But unfortunately, there is no such thing happening in Pakistan for many reasons. Now I come to the alloys of aluminum. So as I already mentioned, there are two types of alloys. There are wrought alloys and cast alloys. And from all of them, there are some are heat treatable and others are non-heat treatable. About 85% of aluminum is used for wrought products, something like plates, foils, extrusions, and other things. Wrought aluminum alloys are these. These are actually already mentioned by the president Dr. Lyat and Tahir also, that these are the series classified by the Aluminum Association. And we have, you can see, this is pure aluminum, and it is good for electrical conductivity. When you are offered to make 2000 series, manganese for the 3000, silicon, and so on. And this is the latest 8000 and 9000, in which we use metals like lithium and zirconium and vanadium. And these are particularly used for space application, aerospace applications. And you can see the 4 of these are non-heat treatable and 4 are heat treatable. Alloys like 2000, 6000, 7000 and 8000 are heat treatable, whereas 1000 and 3, 4, 5 are non-heat treatable. Strengthening mechanism, very well described by Dr. Gulayat Hussain. First, just to recap, the strength of aluminum can be modified through various combinations of cold working, solid solute strengthening, and heat treatment. The cold working process is, rolling, forging, and drawing, wire drawing, etc. So, except 1000 series alloys, additional strength can be obtained by solid solution strengthening, dispersion, and precipitation strengthening. Cold working. In cold working, we produce plates, sheets, wire rods by cold rolling, wire drawing, and other things like that. During cold working, what happens? The number of dislocations and their density increases, and that actually increases the strength of the alloys. Dislocations are already mentioned that line defects, and they play a crucial role in the mechanical behavior of metals and strength and ductility. Dislocation and strength. When metal is subjected to stress, dislocation can move through the crystal lattice, and this movement is known as slip. The slip allows the metal to deform plastically, and the stress required for the plastic deformation is known as yield strength. It is simple. In order to improve the strength of the metal, it is necessary to hinder the dislocation movement. When it is hindered, the strength increases. Otherwise, it becomes like it is ductile metal. How dislocation interact with different species? Like they interact with solute atoms. Solute atoms restore the lattice, and dislocations are restricted to move around the solute atom. Again, the precipitates, it also makes movement. The dislocation has to move all around the particle, all around the precipitate. The dislocation interact with themselves as well. One dislocation intersects another dislocation with another one. Then the grain boundaries, when we reach there, the dislocations, the slip plane is gone. So it cannot move with continuous movement because the slip plane is not available for at the boundary. So it gets stopped there, and another movement coming after it also gets piled up, and the consequences are that dislocations pile up, dislocations locking takes place, and the result is increase in the strength of the material. So once again, the hindrance to the dislocation movement increases the strength. Solid solution strengthening. Certain elements produce distortion in the matrix. They include the dislocation movement, particularly the alloys like 3000 and 5000 series manganese and magnesium are added. They increase the solid solution strengthening of the metal. Then the third is precipitation hardening, already described very in detail. Particles, micron size, submicron size, they are produced and well distributed all around the matrix through a series or combination of heat treatments. These heat treatments, particularly in aluminum copper alloy, they produce precipitates, and dislocations are hindered, and thereby the strength is increased. Heat treatments. So look at the phase diagram of aluminum and copper. The usually 2000 series, we have alloys in this position, that is 3 to 4% copper in alloys. And what we do through heat treatments, with this element, there are two phases stable at this room temperature. That is alpha, it is alpha solid solution, and then the precipitates, the theta phase. What we do by the heat treatment, we heat this alloy to 500 and 500 degrees and bring it to the single phase region, that is the alpha region, and we then give some time and quench it with rapid cooling, which traps the second phase in the matrix, in the solid solution. Then we perform second heat treatment. In this, we reheat the alloy to around 425 degrees Celsius and give a proper time that the second phase, the theta phase, precipitates and is well distributed in the matrix to increase the strength of the alloy. So these are the series of heat treatments, and this is the philosophy to increase the strength of the material. Alloys and strengthening mechanism in generalized, you can see this if you want to increase the strength of 1000 series, you can only do cold working, and other techniques are not valid for this kind of alloy. For 2000 series, you have precipitation hardening treatment and cold working. These two techniques can increase the strength of the metal. Similarly, others in 3000, 4000 and 5000, you just have to solid solution strengthening and then cold working can increase the strength. You cannot apply heat treatments because these alloys are not heat treatable. And the important thing is, do you know the yield strength of steel? It is around 200 to 250. But when you heat it, this value is close to the class of high strength low alloy steels. So aluminum, if you have 7000 series and you precipitation and cold working, you can get the values of the yield strength and which UPS close to the high strength low alloy steels. Now coming to the recent developments, we have crossover aluminum alloys. In crossover aluminum alloys, it's a new design strategy where we will merge the beneficial properties of existing commercial aluminum alloys. These are called crossover. Particularly, it includes aluminum, magnesium, copper, and aluminum zinc crossover alloys. And actually, they form a modified hardening phase that is more stable and under the stringent service conditions, service requirements. They are more stringent, they can withstand the environment, and they do not allow the softening of the alloy. That's why we have developed such variants. The example of this is, as you know that aluminum alloys are candidate for the space materials deployed in space. The solar radiations containing high energy particles irradiate the hardening phase, and because of the irradiation, the hardening phase is dissolved in the matrix and the alloy becomes soft, leading to softening. So in crossover alloys, they develop a chemically complex phase known as a TAW phase, which has superior softening resistance, and this is the latest development, and they develop these machines. Earlier, you know the properties and application well discussed. Recyclability is very important, and other things are important. And you can see the application, extruded channels, different frames, and things like that. And then you have kitchen gadgets. You can have 3D developed rocket nozzle. You have other materials, aluminum alloy used for the space applications. Ports are available. Extruded aluminum for satellite applications. Car frames. Then this sheet metal, aluminum sheet metal is used for making cabinets or camps, moving camps. Drone, frame for the drone, and then number of parts for the aircraft, including from different alloys are used. You get bicycle frame of aluminum alloys, then alloy rings for automobile. The global aluminum alloy market in 2024 was around $250 billion and is projected to grow to more than $400 billion by 2032, with a compound annual growth rate of 6.2%. And what is our share in this market? Nil. No share. Pakistan has no share in this international market, global market. By any use, you can see that it is used for the transportation, the applications like this. This is the share. Thank you.